All right, so schemas. When we mention schemas, we do mention a formal representation of how we're going to break out our data set, right? And what are going to be the names of the data sets, what are going to be the fields in there, how are they going to relate to one another, right? And we are going to choose a particular naming convention and some nomenclature so that we understand what are the different parts of this, right? So we're going to have on the typically, they'll start with the name of the table or data set, right? Section, course, and whatnot. And then the fields themselves are also going to have a nomenclature for all the natural fields, like the things that refer to natural phenomena, real things, tangible things like student names, department names, titles, professors, years, grades. Those are real things representing real phenomena. Those are just going to be in plain text, whereas all the other fields that are either referring to one another or whatnot, like primary keys, are going to be bold, italic, and underlined. Right? Those are going to be primary keys, and foreign keys are going to be the same, but they're not going to be underlined. Right? So bold and italic. We might change the nomenclature as we progress. I'll try to make sure that we always use the same nomenclature. In a quiz or an exam, I will always provide what the nomenclature is so that there is no misunderstanding on how to interpret the schema. Okay, but just so there are different pieces of the schema, and this is how we're going to be referring to them. Now, in the keys and the primary keys and the foreign keys, right? Typically, we think of the foreign key referring to the primary key, right? And we usually conceptually we think of that as a one direction. It is the foreign key who has the value of the primary key, so that it's kind of like a point to it, right? In reality, it really is a two-way direction, right? Because basically the two values are the same, right? If you know one of them, well, you can get to the other, right? It's like, for instance, if you know the student department ID, you can get the department. But you can go the other way around. You can say, well, if I know a particular department, I can ask for all the students who are enrolled in that department, right? So I can go both ways, right? So usually in relational databases, we think of the primary key and foreign key establishing a two-way relationship, right? Unlike you would have if you implement this in Java. In Java, typically the way you would implement this is that you have the parent having a list or an array or a set of all the children, right? So it will have maybe a set of pointers or memory locations of where all the children are. So you can navigate from the parent and iterate over the children, right, and get a hold of all the other subsets, right, of all those childs in that data set, right? And so you can navigate down to the children. But usually you don't have the reference from the child back to the parent. You could, but typically we don't, right? Once you've navigated to the child, right, there's no way for you to go back from the child back to the parent, right? So in Java, usually by default, right, the way we typically implement these things is one directional, okay? Whereas in a database, typically by default, it's bidirectional. You can go from you can navigate from the child to the parent and from the parent to the child. That's another challenge we'll need to deal with later on when we start to mapping these two worlds. We mentioned that there's a couple of things that are implementable in one world but not in the other, right? And there's some inconsistency between the two, right? So that's one of them, which together that we refer to them as the impedance problem of these two data representations. Referential integrity, as I mentioned earlier, once you establish a primary key and foreign key, you are setting up a constraint, right, that the database now is going to enforce, right, that if you try to remove parents that have children that are referring to them, they're going to stop you, right? The database will stop you by default. You can override that, just like you can override deleting a directory that has files in there. You can override it, yes, but by default, it will stop you. You could, for instance, enforce the rule that say, well, if the parent is removed, it makes total sense that all the other relating records, the child records, they also should be removed, right? It might make total sense. Right? We call that a cascade. To cascade an action, you remove the parent, it can cascade down to the children, right? But by default, it's not. You would have to explicitly configure that. Referential integrity. So here's an example where you have two students that are enrolled in the same department, and so referential integrity would stop me from removing that department, right? Because what would happen to the children? They would be left orphans, right? They would be left. They would be left, referencing what? Referencing something that doesn't exist anymore, right? They have a value of 20, and there is no department 20 anymore, right? So we can override this default behavior and say, what do you want to do with these guys, right? What should happen if I remove the parent? What should happen to children? It could be that I can configure it that they should be set to null, meaning I don't know where they're enrolled, right? They're unenrolled students. That might be that might be totally okay if the business rules allow it, or it might be that you change the set, the value to point to something else. Well, then if they're no longer in math, well they're automatically changed to some other engineering field, right? Computer science or something. The value changes to 21. Or by default, it's unallowed. You cannot do that. So cascade actions allow you to override what should happen when you try to remove a parent and there are children that are referring to it. You can cascade whether you're doing a delete, right, or you're doing an update, or you're doing any operations on the parent. What should happen to the parent to the children? So you could, for instance, say that any deletions in the enrollment will cascade delete down to any of the records that are relevant to them. Okay. If you notice here, the enrollment record references the student, right? So if you remove the student, what should happen to the enrollment, right? That should also cascade, right? So if a student is gone, it makes no sense to have the enrollment listed there, right? It should no longer be shown that they're enrolled in any section. They're gone, right? Again, cascade actions could either when you update or delete can also cascade down to the child elements records. Other constraints that can be enforced. You could, for instance, enforce that a certain field cannot be null, right? Meaning, if you register in a system, you have to give me your email. Right? I will not accept a record that does not have an email. Right? So you can enforce things that are certain things are optional and certain things are required. So you could establish certain fields to be not null. I will not accept not null, or key constraints that are referring to other records, and also referential integrity, like I mentioned earlier. Okay. Excuse me. So for the first half of the semester, we're going to be using the SQL language, SQL language, which stands for Structural Query Language, which has been around for several decades and has been kind of the standard mechanism by which we interact with relational databases. It's a pseudo English kind of language that has a kind of its own limitations because it's English. And so the first statement that we're going to be using is how to create these tables, how to create the schema, right? And there's a create table command that allow you to establish the names of the fields, their data types, also any various constraints, also whether you're going to cascade anything. If you remove one of these records, what should happen to all the related records? So here's the simplest of which, right? Where we're declaring the department table. So create table department. And we're declaring several fields here, the DID field and the DNAME field. The DID field, notice that we're saying that it's an integer and it's required, right? So if you try to insert a field here that does not have a department ID, the insert will fail. The department name is it's a string of 10 character long and also required. I need to know the name of the department. And I'm also now establishing a relational constraints. I'm saying that the department ID is the primary key, right? Meaning we are expecting other records to refer to this field. Okay, so enforce all the referential integrity constraints. Here's the student table. We're saying that we have a student ID. which later on we define it to be the primary key, the student ID. We declare the student name to be 10 characters long. It is required. The department is an integer. It's also required. I need to know what department the student is in, meaning we don't allow students to be unenrolled, right, in the department, right? So when you come into the university, you are a declared student. The graduating year is an integer created on. It's a timestamp. You can also use a default keyword where it allows you to give it an initial value, right? And you can, if it's an integer, you can give it a default integer value or default string value or default date. In this case, we are using a timestamp, and we are using default current timestamp. Current timestamp is a keyword in SQL which looks at the current time in the system, right? And in milliseconds, and it sets it as a timestamp in this case. So same thing with the updated on. That means that when you insert the record the very first time, right, it will look at the local time and it will give it an initial value for the created on. It's very, very common to use these created on and updated on as like an audit trail, right? As folks interact with these records, it's nice to know when they were created at first and when was the last time anybody updated these records. Also, we're declaring a couple things here. We're saying that the primary key is the student ID. We're saying that the department up there, the department int not null there, that's going to be actually it's referencing another table, right? So it's referencing the department table, the department ID field in the department table. So we are referencing it. So the department field here, the local department field here, is referencing the DID field in the department table. Okay, and we're saying that if we are deleted, what should happen if the department is removed? We're going to say that we're going to cascade the delete and we're going to cascade the update. Meaning, if the department is removed, the student is removed. If the department ID value changes from 20 to 21, it will cascade to all the students and says, they're still enrolled in the same department. It'll cascade those updates. Also, we're established a couple other validation. We're saying that enforce the fact that the student ID needs to be positive, and the graduation year cannot be less than 1863 when the college was established, right? So you cannot have a graduation year before it was the school was established. Yes.
Since we are not making grad year compulsory field, how would that?
I'm sorry, say again.
Since we are not making grad year compulsory or mandatory field over there.
Yep.
So how would that check?
Yeah. Once it has a value, right? When you set it, it'll validate that it has that value. Yep. Yes.
What is the difference if there is any difference between current timestamp used in created on and on updated on? Because one is italic and the other one is.
Oh no, the italic doesn't mean it's the same thing. It's the same value. Yep. So notice that the one of them is created on when the record is created, only when it's created, whereas the other one is updated every single time the record is updated. So if I rename the course or I do anything, the student, right, it will re-update that the updated value on. Yes.
Is it recommended or required to use different name for the reference keys? The foreign key and the reference.
No, you can name it the same thing. You can name it the same thing, but it's a very common thing to use the meaning of the field. Yeah. Here we have the course table where we're declaring the course data set, where we have the course ID, we have the title of the course. Notice that the first two are required. We also are adding a comment on the field. We're saying that the title is the name of the course, right? Using the keyword comment. It's also very good practice to document each one of your fields, right? So that other folks that are using or modifying or looking at your schema later on, have a clue on what this means. And the department is not null, and we have are establishing a reference between the current department field here that is referencing the department ID DID field in that other table.